Pascal Rodriguez Warnier from Rotman here. He's going to be talking about resource theories of the pragmatist tradition using a particular case study.
Thank you, Adam, and thank you, everybody, for being here on a Sunday. Before starting, I want to acknowledge that this work has been motivated, influenced, and improved a lot by endless discussions with Wayne Myhrvold, Francesca Vidotto, and Carlo Rovelli. What's my goal here? I'm going to argue that resource theories are a good platform for studying in a pragmatist spirit the meaning and employment of some concepts of philosophical interest. The reason is that these theories shed light on the interrelation between agency and physics. I will use in particular the concept of causality as an example and show that my approach leads to some version of causal perspectivalism. For this, I'm going to first introduce the resource theoretical framework, then I'm going to go to a particular theory, statistical thermodynamics, and I'm going to show that if we accept the interventionist or manipulationalist account of causation, plus the resource theoretical framework, this leads us to some version of causal perspectivalism. But what are resource theories? So these are the result of a resource theoretical approach which constitutes a method for theory building. A resource theory aims to explain a given domain of physical systems, making explicit reference to goals, agents, and a series of constraints on knowledge, accessibility, and means, resources. For this, what these theories do is to propose a figure of merit to evaluate how successfully a task can be performed, can be achieved by an agent with a determined amount of information and a restricted set of manipulations available for the agent to exploit a physical system as a resource. The question then is, what are the transformations under the restrictions that I already mentioned that are possible, and what are the necessary and sufficient conditions for a state transition to take place? Bob Köke and collaborators, in a review of the general mathematical framework of resource theories, mentions, just in passing by, that the resource theoretical approach follows the pragmatist tradition, according to which, very broadly speaking, because you all know, to understand the meaning of a concept is to understand how it is used, under which conditions it applies, and what are its practical consequences. Analogously, for this case, understanding a phenomenon is knowing how agents can use it, intervene in it, to get the desired result. As an approach for theory building, the resource theories differ from what has been called also the dynamicist approach. Just to understand the difference between these two, for the dynamicist approach, the goal is to provide the kinematical structure and to find the dynamical laws to describe the behavior of a system in isolation. That is, without making any reference to exogenous variables, external variables, or agents. Resource theories aim to describe, as I've been saying, how a physical system in a given domain can be exploited as a resource for agents to achieve tasks. For this, they must make an essential reference to external variables, so they describe how the system evolves given some different values that the external parameters can take. For this approach, the ultimate goal, I think, is to learn about the structure of the world in a way that is independent of what will be a deeper theory. So, I think that unlike the dynamical or dynamicist approach, the resource theoretical one provides right from the beginning the tools to do physics from what has been called an embedded perspective. And the reason is that in the dynamicist approach, agents are just the product of many stages of hierarchical organization. That is, human beings are just the result of the evolution of the universe. And the point that I want to make with this is that the arrow of constraining or explanation goes only from the physics towards agents. It's because the physics has been like blah, 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 that agents are in such and such way. In the resource theoretical approach, the arrow is bidirectional. So we have agents that can perform that have some available manipulations to them. These manipulations are represented by sets of transformations that are allowed in a state space of the system. We have the idea that some operations are free and then can be done unlimitedly, while the rest of the operations have a cost. So given the set of operations, the states that can be prepared for free count as resources. The point is that what are the manipulations, what's the task, and what's the information that the agents have to perform these transformations are constraints that go from the agents towards the physical world. But the physical world also constrains what agents can do. The physical worlds provide the state space. It is because of the physical world that we cannot do unlimitedly every manipulation or every transformation. We have some of them that are going to have to be resources, and some others are going to have to be free. It is a consequence of the world, how the world it is, the constraint that the world imposes on what we can do. From the physical world towards agents, we have also, importantly, but I'm not going to be able to delve into them, into this issue, the constraint of the time scales and the equilibration scales. This means that we can do physics, in particular thermodynamics, because things tend to equilibrate at different rates. Even if some of those equilibration scales are going to be more important for us than others, it is a feature of the world that different things equilibrate at different rates. And then, of course, from the physical world towards agents, we have also the laws of physics. Think about, for example, the second law of thermodynamics. This framework, I claim, gives us lots of freedom to play. We can choose to vary the set of manipulations that the agent can perform, leaving everything else equal, and this will give us insights about the dependence of what is achievable, how successfully you can perform the task, on the coarse graining of the manipulations. Depending on the set of manipulations, you will be able to achieve with more or less success the goal. We can also choose to change the amount of information the agent has about the system, and this will tell us about how information can be used to enhance the success of a task. Or we can leave the same set of the manipulations and the information invariant and change the theory, and this will give us insights about the limitations of the theory. So think about all this research trying to distinguish what's special about quantum mechanics with respect to superquantum theories or classical theories, and this will give us also insight about the intertheoretical relations. But I think that it's very important to keep in mind that resource and dynamicist theories are not mutually exclusive. The two approaches have just different purposes, and I think that anybody that claims that one is the unique and right to do physics is wrong. In fact, many times the resource theoretical approach is used as a first stage for understanding phenomena, having some constraints to build then a dynamicist theory. So far we have been talking about the resource theoretical framework. Let's look at a particular resource theory. As Myhrvold has argued, thermodynamics was originally built as a resource theory, and researchers are now explicitly returning to that original approach, especially with the advent of quantum thermodynamics and quantum informational techniques. One way to characterize the statistical thermodynamics is as the science of the expectation value of energy exchanges in terms of heat and work. For this, clearly it is required a distinction between what counts as heat and what counts as work. It is widely assumed that the energy exchanges due to the manipulations of the external variables count as work. So in statistical mechanics or statistical thermodynamics, we have a Hamiltonian, which is parameterized by a series of external parameters. Every exchange of energy that is due to the changes in the Hamiltonian because these external parameters change are going to count as work, and the rest is going to count as heat. Doing work is, as Maxwell defines it, changing the configuration of a system against a resisting force, and heat is the spontaneous energy cost due to the response of the system given the manipulations. So, very generally speaking, just as much as I need, the first law tells us that the expectation value of the internal energy change over a process equals the sum of the heat and work exchanged. The second law, a version of the second law, tells us that it's not possible to reliably exceed Carnot's bound on the extraction of work over a cycle. And from these two laws, it follows the work-energy relation, which states that if we have two equilibrium states, the minimum value of the expectation value of work needed to carry a transition between these two states would be, if the process is reversible, equal to the difference in the free energy expectation value of the free energy minus the Gibbs entropy difference between the two states times the temperature. Another way to think about this, but it's the same, is that if we have a heat bath at constant temperature and we want to extract work from it, this work-energy relation will give us the expectation value of the maximum amount of work that we can extract from it. Equality holding only for reversible processes. To illustrate this, I'm going to use the Sealer engine example. Some of you may be already familiar with it. So we have a one-molecule gas in a box coupled to a heat bath at constant temperature. We put a partition in the middle such that the molecule ends up being either on the right or the left of the partition, and we can use the partition as a piston. We can move it either to the right or to the left to extract work or to do work on the environment. The question is then, can an agent that doesn't know whether the particle ended up, after putting the piston, ended up in the right or left side, extract work from the system? The issue is that the expectation value of the work that this agent will be able to extract will be 0, because sometimes he will have to do work, others he's going to be extracting work, but the expectation value will be 0. And then this quantity on the right side, which is also called the free energy, and takes the minimum value when the system is in equilibrium, will also be 0. Now, let's give this agent that has the same set of manipulations available to them information about where the molecule is. Now, the agent will be able to extract energy reliably, a positive amount of energy, which means that there will be free energy available for them to be extracted. So the system will not be in equilibrium, because, as I just said, equilibrium is associated to the minimum value of free energy. Let's have a third case in which the agent has information about where the molecule is, but the set of manipulations are restricted. Now they can only move the piston just to the right. The expectation value of the work extracted is going to be half than in the second case. So the free energy available for the agent to be extracted is going to also be half of it. The lesson of this example the important thing for the purpose of this talk is that whether the agent can reliably extract a positive amount of work or not depends critically on the information about the state of the system and the manipulations available to them. Okay, let's move now to causation. I'm going to take the manipulationist and interventionist account of causation as synonymous. And I think it's the most suitable one for studying the resource theoretical approach, according to which A causes B if surgical changes in A, cutting any correlation between A and its causal past, leads to changes in B, with all the rest staying equal. So causation in this view requires external parameters because we deem B to change only if A changes when it's manipulated. And to form causal judgment, if B can take two values, say 1 and 0, if B changes or not, we need to be able to distinguish whether B changes or not. And for this, effects have to be stable. This is going to be a move that I'm going to take. I'm going to associate effects with records that need to be more or less stable. As General Ismail has said, what you think as the effects of your actions are just the future records of their occurrence. Typically, we use the word record to refer to the result of changing the configuration of a system against a resisting force for a period of time, if we are considering cases such as the Sealer engine, where we have one heat bath at constant temperature, meaning if we are thinking about isothermal processes. The record, that is the effect, must have some degree of stability. Two reasons. One, because we need to be able, as I said, to judge whether B changed when A changed. And the second one is nobody will want to claim that non-stable phenomena, fluctuations, are records. So the point, if records are associated with effects, what we deem as human beings to be useful records require the expenditure of energy. In the case of if we have one heat bath, this will be in the form of work. If we have systems at different temperature, expenditure of energy will be in terms of dissipation. But this comes, I think, naturally in my proposal, because in statistical thermodynamics, work is identified with the exchanges of energy due to the manipulations of the exogenous variables of the systems. Records, which I am associating with effects, require then the expenditure of work if they are created isothermally. And the longer lasting the record is, the more work is needed. Causation then is identified with the possibility of making changes if we have a heat bath against a resisting force that will not occur but mere spontaneous evolution. This means that a necessary condition for a causal process to actually take place in the world is the availability of energy. And here we have a tangible connection with the Sealer engine. The task, paraphrasing Woodward, is making the effect happen, and we have identified the effect with a record that requires, in this context, work. The extent to which the task is achievable then depends on several factors. There must be energy available for the agent to do work on the system, to do work on the environment or extract work, and this energy will be relative to the manipulations available and to the information of the agent. So relative to some conditions, the agent will be able to carry out a causal process, as the Sealer engine case exhibits, and relative to others, the agent will not be able to carry out the process. And this, I think, comes natural if we think that causal processes to take place, a necessary condition is non-equilibrium. Because if the systems are if everything is in equilibrium, then nothing changes, no causal processes take place, and whether the system is in equilibrium or not is not an absolute matter. So if we use the resource theoretical approach as a platform to study how causality is used and what are the necessary and sufficient conditions for it to be successfully employed in relation to thermal phenomena, then we find that the manipulationist account of causation leads to some sort of physical perspectivalism. And this perspectivalism does not allude at all to the error of causation, although it is compatible with it. But I think that there is more for perspectivalism than just the issue of the arrow of time, as there is more for causation than just the issue of its asymmetry. Another perspectivalist element, which is the one I'm pointing out, that we have not paid too much attention, is whether a causal process is possible or not will depend on both agency and physics. And the satisfaction of necessary and sufficient conditions for A to cause B, at least partially, depends on the perspective of the agent. And the perspective of the agent is going to be determined by the coarse graining of the manipulations and the information available to them. Two caveats before concluding. Energy may not play a relevant role in many of the descriptions, explanations in more fundamental theories when they are cast out in the dynamicist approach. And this is fine, I think, because this work doesn't aim to claim that causation is fundamental or a necessary condition for a physical theory to be built. And the second caveat is maybe causal processes do not play any role in the dynamicist tradition at all, since for the manipulationalist or interventionist account of causation, external variables are necessary, and as I said, the dynamicist approach aims to model systems or to describe systems without making any reference to any exogenous variable. Final remarks. To conclude, there is an alive and flourishing approach, I think, to theory building that is pragmatist in spirit, which philosophers can use to do first-order research about the interplay between physics and agency, as well as to study the significance of abstract general concepts typically appearing in the philosophical jargon. I have shown that this can be done with the concept of causality, I think, because causal claims now are possible in this domain. To evaluate whether causal claims are possible, we need to incorporate both agential elements and elements about the world. Because of this, I think that one lesson that pragmatism should take is that attempts to fully reduce causality either to agency or to the physical world fall short, and we should try to overcome the temptation of falling into this dichotomy of thinking that some things are only physical or agential and not part of both. Thank you very much.
Thanks very much, Pascal. That was a terrific talk. I think I might have lost track of one of the ifs or only ifs, so you might just have said this in the talk. But on your view, does this mean if I need to talk about causation with respect to physical processes, I have to be able to conceive of whatever mediating physical theory is in play as a resource theory? So suppose I had some agents who could like smash planets together hard enough to generate like gravitational waves that smash the Rock of Gibraltar. Can I only talk about that as causal if I can sort of reformulate GR as a resource theory?
Okay, thank you. I think that you are already, if I understand correctly the question, you are already talking about agents doing some things and seeing the effects. I think that a resource theory, that situation will have to be modeled ideally, or the best way to model it will be in terms of a resource theory, because you have these external agents that if you model the agents, then within the theory, then you won't be able to get a causal account of that process. Okay. Am I answering your question?
Yeah, thank you.
Excuse me. All right, that was really fantastic, and there's lots of things I'll hopefully talk to you about maybe over the coffee break. But I also wanted to point out there's somebody that I think counts as like a really sort of small, underdeveloped pragmatist in orientation. Georg Henrik von Richt has this book, Explanation and Understanding.
Sorry, can you say the name again?
The last name is von Richt, V-O-N. I can also email it to you.
Mm-hmm.
W-R-I-G-H.
Yeah, I got it. Thank you. Yeah.
I think it's from like the 60s or 70s. He's one
Uh-huh.
of the very first people to talk about causality in this context of like physical stuff, and how whenever he's got this stuff about like putting nature through its paces, the things that it wouldn't do unless you intervene to make it do that, and how there's thus always something kind of outside of whatever it is that you're doing with your sciences in a way that's really similar to what you're talking about.
Mm-hmm.
So it might be really helpful, like additional pragmatist grist for this mill.
Thank you very much. Is this the fund director of, that does philosophy of probabilities? Okay. Thank you.
Mike.
Thanks for the very nice talk. So just wondering, so first two short questions. So first quick question. So there's been in philosophy physics, there's been a lot of debate about principal theories versus constructive theories. And I'm wondering, is there a connection between resource theories, the way you're describing them, and principal theories? And then the other short question is, what do you think of it? So you mentioned the connection between dynamicist approaches and resource theoretic approaches. You said they're complementary. Complementary. And but then you mentioned, so in the case of statistical thermodynamics, we've kind of come back to the resource theoretic approach. So I'm wondering, is there like a strict, like, do you need a dynamicist completion of a resource theoretic approach? Do they always come together, or sometimes required?
Yeah, thank you. So regarding the principle versus constructive theories, well, I mean, I will have to think more about it, but I think that in principle, the principal theories are associated more with the resource theories because you start from some phenomenological claims or things that you can do, way more operational, and then you study what you can do or how these constrain the future construction of a possible constructive theory. I don't think that, I mean, you have cases in which you have just resource theories and not dynamicist theories or constructive theories. I think, if I understand correctly, for example, some people working in quantum reference frames are just building a resource theory, and that will help in finding or articulating a theory of quantum gravity, but there is no definite or theory of quantum gravity. But I think that what they do is still legitimate and a good enterprise. So I don't think that they have to be necessarily hand by hand. But I do think that to complete a project of description of a physical domain, probably you will want to have both a resource theory and a dynamicist theory. A resource theory that would that will help you to understand, for example, what causal connections can you make, how causation would work in this domain, and you may want a dynamicist account that will not make any reference to agents or constraints or anything like that. I think both of them are important, but it happens that not necessarily both of them are fully developed at the same time.
We've got time for, we'll go with Armand.
Hi there. I appreciated the talk. So I do think resource theories are interesting. I'm less convinced that they're interesting for talking about causation. So here's the question.
Sorry, you are not convinced, or you are?
I'm not convinced about the causation aspect. I'm convinced about generally resource theories. But anyway, so here's the question. So I get that resource theory will package things nicely and tell you what an agent can actually do given certain information or whatnot. But isn't all of that just straightforwardly extractable from a non-resource theory, which tells you about causal connections? So I mean, I'm not seeing that in that kind of case it gives you anything that you wouldn't already have without a resource theory. So just wondering what you thought about that.
Yes. Okay, I will tend to think that in a non-resource theory you can do any transformation that the physics allows you. And then you can see what transformations are possible in the theory, what solutions of the equations are, but what are the solutions of the equations of the theory. But if you adopt a manipulationist or interventionist account of causation, I think you need something like resource theories, because by definition, you need to make reference to external parameters that I'm not sure how they fit in a dynamicist theory that tries to model everything. So I take the dynamicist theory to try to model a physical domain without making reference to anything external, but by definition of the interventionist account of causation, you are asking how things change in reference to changes in these external parameters. So I don't see, I'm not sure how can you do a causal analysis of the dynamicist theory in interventionist terms if you don't appeal to these external, without appealing to these external variables. I'm not sure if I'm answering your question.
No, I think you are. I disagree, but correct, it's time to end.
Yeah,
Thank you.
We're just at time for coffee break now, so let's thank Pascal.